Okay, so now we're going to move into something that's a little bit kind of outside the realm of what is considered chemistry. We're going to move into something that is more physics, and there's a reason for it. We're not trying to make your life difficult. We're going to talk about something called electromagnetic radiation, and most people hear the word radiation and they kind of panic a little bit. But what electromagnetic radiation is, it's energy that is generated by a quantum electronic transition in an atom. It means the electrons are moving around. And radiation, it's actually, there's a lot of different forms of it. So in order to talk about radiation, though, we have to talk about what it is, and it's a wave. Energy comes in waves, matter comes with mass. Okay, so they come in different forms. And when it comes to measuring waves, and that's what we're talking about, waves. I'm not very good at drawing them. Amplitude is half the distance from the top to the bottom of the wave. So if you ever listen to AM radio, that's amplitude modulation. They're adjusting how tall the wave is. Wavelength is this funny looking thing, looks like kind of an upside down Y. It's referred to as a lambda. It's a Greek letter L, and it's literally a length, horizontal distance. If you took out a ruler and you measured it in meters, it is a length from the top of a wave to the top of a wave, or the bottom of a wave to the bottom of a wave. Okay, and it's measured in meters or nanometers. Frequency is kind of a weird thing. It's the number of peaks that are referred to as cycles that pass through a given point in a specific period of time. So it's not speed, but it's how many hills pass through a point in a given period of time. So, let me erase that stuff. All right, so on this one, amplitude is half the height or half the depth. The wavelength is the distance from the top of one to the top of the other, or the bottom of one to the bottom of the other, literally with a ruler. That's the wavelength. Now the frequency is a little bit strange. So the frequency, if this was 1 second, and this wave, keep in mind this wave is moving, okay? It's in motion. And as it moves through this area, in 1 second I have 1, 2, 3 cycles. So 1, 2, 3 cycles of the wave pass through this area in a second. So 3 cycles per second. The units are 3 hertz, or sometimes it's written as 3 seconds inverse, or 3/1 seconds. Okay, but hertz is most commonly used. It's abbreviated HC. It's not the car company. Okay, so a high frequency wave, can you see that in a period of time there are 1, 2, 3, 4, 5, 6 waves, 6 cycles, whatever that time period is. Here I've got 1, 2, 3. Here I've got 3 waves. So this one has a low frequency, and this one has a high frequency. Okay, and so this is to show you what it looks like. A radio wave literally is electromagnetic radiation, and it has a very long wavelength, over 6 feet. Okay, it has a very small frequency. Red light, which is what you see in a neon sign or a stoplight or anything like that, has much shorter wavelength compared to radio waves and a much higher frequency. And then if you look at an X-ray, X-rays have a much shorter wavelength and a much higher frequency. So what you should notice is that low frequency equals long wavelength, and high frequency equals short wavelength. So they're inversely related to each other. One big and one small. So all light is referred to, all electromagnetic radiation, we're going to call it light. And some of it we can see and some of it we can't. The speed of light is a constant in a vacuum. It's 3 times 10 to the 8th. We're going to call it 3 times 10 to the 8th, not that number. Depending on the medium it's in, if it goes through air, it's a little different. It goes through water, it's a little different. It goes through glass, it's a little bit different. But we're just going to pretend it's always in a vacuum. And this is talking about the speed, like as in miles per hour, it's meters per second. It's different from frequency. Frequency is cycles per second. How many hills in a unit of time, as opposed to how much distance you travel in a unit of time. Oh, I don't want to do that. Okay. All right, so wavelength can be calculated, or the frequency can be calculated from the formula where C equals lambda times frequency. And I use F to symbolize frequency, even though there's really this funny little shape, and I don't know how to make it very well, so I'm not going to use it. I use F. So C equals lambda F. Here's the electromagnetic spectrum. You guys are going to do an online simulation with this. Here's really long wavelength and very small frequency. Here's very high frequency and very short wavelength. Okay? And this is literally all the different forms of radiation. You're going to see radio and TV. Then microwaves are falling in this kind of range. Infrared is in here. The visible spectrum is a very small little chunk, and right next to it is ultraviolet. And then you have X-rays and then gamma rays. Okay? And so that's how the radiation breaks down. You've heard of Roy G. Biv before. The reason we use nanometers is because visible light falls into a range of about 400 to 700 nanometers. So, sample problems. If I give you this, I give you the conversion, I give you that conversion, all it is plug and chug. So, red light has a wavelength. You need to know that stands for the TP thing. Calculate the frequency. So, C equals lambda F, 3 e to the 8th equals 6.35 e to the negative 7 meters times the frequency. Now, this is an important thing. If you're going to use this equation, wavelength has to be in meters, frequency has to be in hertz. It can't be anything else. Okay, the equation doesn't work like that. So if it's something other than meters, or it's something other than hertz, then you need to fix that before you use the equation. So all you're going to do here is divide. 3e to the 8th divided by 6.35 e to the negative 7. And frequency equals 4.72 e to the negative 4, or e to the positive 14 hertz. Okay, it's important to include that in there. Okay, I'm going to start, I'll notice when you're doing a quiz or a test or a homework, I'll be like, wait a minute, you're missing the E something. They're almost all of these are going to have some kind of an E something on them. Okay, so radio station has a frequency 91.91 megahertz. So before I do anything, I'm going to change 1 megahertz into hertz. Okay, because to use this equation, my frequency has to be in hertz. So 3 e to the 8th equals the wavelength times 9.11 e to the 7th. The wavelength is going to be pretty long actually, because this is a radio station. Yeah, so 3.3, and then the units would be meters. That's about 10 feet. It's a pretty long wave. Okay. Okay, blue light has a wavelength of 440 nanometers. Again, before I do anything, I'm going to change from nanometers into meters. And then I'm going to do the equation. So 3 e to the 8th equals the wavelength times the frequency. Again, I'm going to divide. Almost all of these you're going to divide. And you get 6.82 e to the 14th. And again, watch out for that. Make sure you include it. Hertz. Okay, so now, how does this all relate to energy? Okay, because radio waves, they're not harmful. You've been bombarded by them your whole life. But things like X-rays and gamma rays and even ultraviolet have the potential to do a lot of harm, and that's because of the energy that's associated with them. So light comes in these packets of energy. They're referred to as photons, much like compounds come in single things called molecules or atoms. And packets of energy are just the smallest chunk of light, really, and it's called a photon. All right. The energy of a photon is the product of the frequency and something called Planck's constant. There's a lot of math involved with how they came up with this, but that's basically the equation. So the energy equals the H value, which is right here, and I'll give it to you, multiplied times the frequency. So it's just another equation. If I rearrange it and I put in wavelength, if I take the C equals lambda F and I divide by lambda and I divide by lambda, F equals C over lambda, and then I can plug that in for F, and so I get another equation here. Okay, either equation is fine. They're derived from each other. Doesn't matter which one you use. So it says calculate the energy of a photon that has a frequency of 101.5 megahertz. So that is frequency. And again, it can't be megahertz. 1 megahertz is 1 e to the 6th hertz. So I get 1.015 e to the 8th hertz. So that's the frequency. Since I have frequency and I want energy, I'm going to use this equation. E equals the h times the frequency. So the energy equals 6.626 e to the negative 34. The units on this are a little weird, but you'll see what they are in a minute. And instead of hertz, I'm going to write 1 over second because that's what it is. Okay, so when I multiply that out, I get 6.73 e to the negative 26. And then the units are, if I have joules seconds and I multiply by something 1 over seconds, the units are joules. And so this is the energy of 1 photon of light. Now keep in mind that's really, really small. Okay, not a ton of energy because it is a radio wave, but it's measurable. It says calculate the frequency. So now I'm looking for the frequency when I give you the energy. So again, E equals HF. 3.25 e to the negative 19 equals, there's my h, multiplied times the frequency, so all I'm going to do is divide. And you get 4.9 e to the 14th. And the unit for that would be hertz, or 1 over seconds. Okay, so it's pretty much plug and chug. It's not too hard. The biggest thing is trying to recognize what units you have. So here I have energy, and here I have wavelength. That's not frequency, that's the little teepee guy. So before I do anything, can't have nanometers. So 1 nanometer, 6.35 e to the negative 7 meters. Now there's a couple of ways to handle this, but since I'm looking for energy and I have wavelength, I'm going to actually use this equation, hc over lambda. And all I'm going to do is plug in my constants, 6.626 e to the negative 34, 3 e to the 8th, over my wavelength, 6.35 e to the negative 7. Now make sure you type this in properly on your calculator and you use that exponent button. It should be very obvious if you don't get the right answer for this, if you start getting some really weird numbers. And so this one, the energy is 3.13 e to the negative 19 joules. Okay, remember you want to use the E button, not the times E button, anytime you're dividing by something that is written in scientific notation. Okay, so just be real careful with that.